In this lesson, we'll be solving linear systems using substitution instead of graphing. The substitution method is another way to solve a linear system using algebra. This method requires you to write both equations in the slope y-intercept form, which is just our standard y equals mx plus b. What we're doing here is we're establishing that once everything is written in y equals mx plus b, we have two equations that equal y. If the two equations both equal y, then we can say they are equal to one another. Here are two equations whose lines we are told will intersect. Y equals 2x plus 7, y equals negative x minus 11. They are both equal to y, therefore we can state that they are both equal to one another. That is, 2x plus 7 is equal to negative x minus 11. Now that we only have a single variable, x, we can solve for x. We simply collect all of the x terms on one side and put all the numbers on the other side. This leaves us with an equation that reads 2x plus x equals negative 11 minus 7. Further simplifying gives us 3x equals negative 18, and a final value for x of negative 6. Once we have this value for x, we can take its value and plug it back into one of the original equations to solve for y. We'll use the first one. So y equals 2 bracket negative 6 being substituted for x plus 7 will give us a coordinate, an answer for the y value of negative 5. So now we have a point of intersection which is negative 6, negative 5. Here we're given two equations, 6x plus 2y equals 12, intersecting with 4x minus y equals 5. Now both these equations are not yet in slope y-intercept form. So the first thing we need to do is put them into that form. 6x plus 2y equals 12 can be rewritten as 2y equals negative 6x plus 12. Further simplifying gives us an equation y equals negative 3x plus 6. This is now in slope y-intercept form. Looking at the other one, 4x minus y equals 5 gives us negative y equals negative 4x plus 5. Further simplifying to y equals 4x minus 5. Both of the right-hand side of these equations equal y. Therefore, once again, we can say that they are equal to one another. Now that we have an equation with only one variable, we can solve for x. Which gives us a value of x of 11 over 7. We could take that value for x, plug it back into one of the original equations, and come up with a value for y. Another example, x plus y equals negative 2, intersecting with x minus y equals 6. Once again, these are not in slope y-intercept form, so we'll just have to make a few adjustments to get them into that form. X plus y equals negative 2 becomes y equals negative x minus 2. Now it's in the correct form. X minus y equals 6 becomes negative y equals negative x plus 6, further simplifying to y equals x minus 6. Now that they're both in the same form and both right sides equal y, we can say that they are equal to one another. Simplifying and solving for x gives us a value of 2 for x. We can take that value and plug it back into one of the original equations and solve for y. Doing so gives us a value of -4 for y. So now we can say that our intercept of these two equations is 2, -4. Use the equation of the line in the y equals mx plus b form. Substitute the value of x from step 1 into that equation. Solve for y. Well, we've already been doing this, but this just kind of isolates this one step. So y equals x plus 5 when x equals 2. We simply plug the 2 into the equation and gives us a value of 7 for y. Y equals 6x minus 3 when x equals -5. Again, we just plug the -5 into the x portion of the equation and gives us a value of -33, and therefore gives us an intercept, or a coordinate, sorry, of -5, -33. Next example, the equation y equals 3x plus 8 when x equals 7. Again, we're simply substituting x with the value 7, giving us a value of 29 for y, and therefore a coordinate of 7, 29. Last example here, y equals -9x minus 25 when x equals 4. We sub the -4 in for x, and we're given a value of 11 for y. Therefore, our coordinate is -4, 11.